So we've all completed the Electrostatic Forces Discovery Lab. At least collected some data where the question becomes is can we mathematically predict the magnitude of the electrostatic force between two charged objects? And with this lab, you were able to manipulate the charge of each of the individual objects, and then kind of see the effect that it had on the forces between them. And then you were able to manipulate the distance between the charges and see what the resulting effect that it had on force. Now, if you changed up your charges and distances appropriately, you should have been able to see a pretty clear mathematical relationship on the effect that each of those had. So the first thing I want to do is take a look at the challenge one, where you manipulated the magnitude of the charges but kept the distance between the charges the same, and see what conclusions you had. So, Aiden, what did you conclude was the effect that changing the charges had on the magnitude of the force?
For the top one.
For the challenge one, yeah, this one. What was the trend that you saw as you changed the charges? What happened to the forces?
I just saw that as they were getting further apart, that the force was bigger.
So you mean what do you mean far apart? Like as we increased the charges? Is that what you did?
Or I had
because when you say far apart, you're talking about distance. We're not changing distance in this one.
Or I had the higher the charge for the.
So the greater the charges,
yeah.
The bigger the force.
Yeah.
Yeah. Did anybody see that also? As you increased the magnitude of the charge on any of them, if you just increased on one, but increased on both, you should have seen that there was an increase in the magnitude of the force. And when we're doing mathematical modeling in science, when we're trying to develop an equation that represents, what's going on here, these are the things that we look for, and we call this a direct proportionality. Whenever there's a direct proportionality, we know that whatever factor we're changing is going to be in the numerator of our equation. So if this is my electrostatic force equation, I know that charge is going to be in the numerator. And it is. And in fact, the product of the charge is in the numerator. How we know it's not like the sum of the charges? Well, this again is a mathematical relationship too, and don't want to dig into that too deep, today. But the greater the charges, the greater the magnitude of the force. That's a direct proportionality. But you probably even would have seen too that if you doubled one of the charges, what happened to the force? Did anybody do that? If you just doubled one of the charges, what happened to the magnitude of the force? It doubles too. If you tripled one of the charges, you would find that the force tripled. If you quadrupled one of the charges, then the force quadrupled. If I doubled both of them, then my force would quadruple. So this is a direct proportionality. Anything I do to the charges is exactly what happens to the force. Double a charge, double the force. Triple a charge, triple the force. Direct proportionality. So I don't have to do anything to these values other than just represent the product of these two charges, Q1 and Q2. Okay, so this is our relationship between the charges and the force between the two charges. The greater the charges, the greater the force, and they're directly proportional. So if I double one of the charges, I'm going to double the force between them. Okay, if I double both of them, then that's quadrupling my numerator, and it's going to quadruple the force. You'll have to do this. Expect that on a quiz that you're going to have to is like, hey, what happens if I double the charges? Or triple the charges, quadruple the charges? You're going to need to be able to respond and saying what the effect on the force is going to be. Good. All right. So then the distance. So then the challenge two is we kept the distance. The charge is the same, but then we varied the distance between them. And what trend did we see here? Braxton.
If the force was lower each time the distance is gained, but I can't figure out the actual
Mathematics behind it, and we can start there. So, did everybody see that as you increase the distance between them, that the magnitude of the force decreased? If the distance goes up, the force went down. This is an inverse relationship, but it's not perfectly inverse. If you would have doubled the distance, it's not like the force was cut in half. What you actually would have seen that if you doubled the distance, the force would be 1/4. If you tripled the distance, the force would be 1/9. If you quadrupled the distance between them, the force would be 1/16. Okay, this follows the inverse square law. And I want you to, include this either in your notes or on your lab, wherever. But this is the mathematical relationship. I think if we would have really looked at it and compared those numbers, or even graphed it, which we could have done, we would have seen an exponential, an inverse kind of scenario where 1 over our distance squared. Okay? So this becomes our relationship between the distance between the charges and the electrostatic force. Isn't it interesting? You can't not recognize how closely related our relationship between charges and force are, and our relationship between masses and gravity is. The equation's almost identical. This one's just dealing with electrostatic forces, the repulsive or attractive force between charges. Now, instead of G, like we had in our universal gravitation equation from Isaac Newton, we have a K value. A K value. This is a constant. And I do refer back to the universal gravitation lab that we did way back when we were discussing Isaac or Newton's laws. If you remember that lab that we did, we had a simulation, and it looked almost like the SPET simulation that you did, but it was masses instead, and we changed the distance between the masses. We changed the masses themselves, but in that lab, we actually graphed the relationships to figure out what this constant was, and it was 6.6 times 10 to the negative 11. Okay, and it was a magical number. And it still remains a magical number. In science, we have no clue what it actually represents. The same thing is true for electrostatics. We now have a number that was experimentally determined the same way as it was with the universal gravitation. Okay, we've got this was experimentally determined. I could do a lab with this simulation where we could graph F times d squared over the product of the charges. Okay, just like we did with the gravitation lab, and we would find that the data that we would have would be linear, just like we did with the universal gravitation lab. When we took the slope of that, it would be 9 times 10 to the 9. Whoops, gosh, I can't even write. That would be the number. If we did that, if you went to the simulation, you graphed those things, and took the slope of it, very similar to what we did with gravitation. We would come up with a magical number of 9 times 10 to the 9. What does this number represent? Well, theory suggests that this number represents numerically what we kind of describe as how these charges are distorting the space around it. It's just a number that represents something that we have no clue that's going on. But it's a perfect number. It's very much fine-tuned. If it was any different, matter itself could not exist. If this was any bigger, the nucleus of an atom could not exist, which means matter can't exist. If this number was even changed slightly. Because if this was even increased by the slightest amount, the force between the protons and the nucleus would be too great, and they would actually scatter. Isn't it kind of, I don't know if you've ever thought about this, but if protons repel each other, how does a nucleus even exist? How does that happen? I mean, protons don't want to be near each other. How does that exist? Well, this electrostatic force is trying to repel those protons, but there's actually another force. It's called the strong nuclear force that holds them together. You may talk about that if you get in chemistry or whatever, but there's a strong nuclear force that holds them together. That strong nuclear force actually has its limits, And if this was even slightly bigger, that strong nuclear force would not be enough to hold that nucleus together. It would annihilate, and matter would not exist as we know it right now. It's crazy to think about how magical that number is. So anyway, so here's our equation. This is called Coulomb's law. And this equation is effective in quantifying the magnitude of the force between any two charges. Okay? And I emphasize the word magnitude. A lot of times, if you looked up Coulomb's law, you might see it expressed as an absolute value in the numerator, because a lot of students get so fixated on positive versus negative. Even as I walked around and saw some data that students had, some of us were putting positive and negatives in the charges, which is fine. It's not gonna hurt anything, but the only thing that positive and negative is gonna help us conclude is whether it's repulsive or attractive. That's it. That's the only thing that the positive versus negative is going to do. So this equation is strictly about the magnitude of the electrostatic force. The positive versus negative will just help us conclude whether it's attractive or repulsive. That's it. Okay? We're going to be practicing that. Before we do that, we are going to go through a little lesson. So if you want to put that lab away. Really quick lesson. In fact, most of what's on this lesson is stuff we've already talked about, so I'm going to go through it kind of quick so we can get to practicing this equation. Just to review, and I'm going to point out that there's some very important reminders on this slide. Some of you may want to go back through some of it because I know we're not quite there yet. This one should go without saying, but this slide, is just reminding us that we've got positive and negative charges. Okay, got to remind ourselves where they come from. The charge of a single electron is 1.6 times 10 to the negative 19. The charge of a single proton is 1.6 times 10 to the negative 19. The difference is that electron is negative and the proton is positive. This symbol you'll see, this E with the negative power, whatever, is actually the symbol for electrons. So if you ever see that as you're reading, or if you see me writing that, that just means electron. I wanted to also show that if we had a full Coulomb of charge, so like a Coulomb's worth of electrons, it would be 6.25 times 10 to the 18 electrons. That many electrons to be a full Coulomb of charge. That is a lot. We're going to talk, once we get into current electricity, we'll get a little more perspective on this, that if there was a full Coulomb of charge moving through a conductive pathway as current, it would carry an insane amount of energy with it. Very, very dangerous. So we don't see that very often, a full Coulomb of charge moving, but that's what it would look like. I wanted to be very intentional today about representing Coulomb charge in different ways. Okay. You're going to read problems starting today, okay, where you're going to see something like microcoulomb, and you've got to know what that means. You've got to know the prefix micro is 10 to the negative 6. So if I have 5 microcoulomb, a problem says there's 5 microcoulomb of charge on this object, you need to know that that's 5 times 10 to the negative 6 coulomb. We have to convert that when we use our Coulomb's law equation. Okay, these Q's have to be converted to full Coulomb. So 5 microcoulomb would be 5 times 10 to the negative 6 coulomb. Nanocoulomb, we'll also probably see. If I had 5 nanocoulomb, little nc, it's going to be 5 times 10 to the negative 9 coulomb. Okay, this page is on the PowerPoint that's posted on today's Canvas page, but you might want to have that written down close by. In your notes as you're working through some problems that we're going to be doing. Okay. Already talked, again, a lot of this is some review. Whenever, electric charge exists on objects by separating charges that were originally a part of neutrally charged objects. Okay, it was brought up today about do we make the assumption that all objects are neutral prior to charging? The answer is yes. So whenever we do have a charged object hanging around, it had to have been transferred from one object to another. So however many electrons move over is now how much net charge an object is, on those objects. Okay. This is our lab that we did. We've already talked through this, but it's just up here also, so you have access to it. You can go through. We already made these conclusions with the lab. The electrical force between two charges is directly proportional to each charge, inversely proportional to the square of the distance. That's how we say that. Inversely proportional to the square of the distance, and that is Coulomb's law. There it is. Coulomb was the one who came up with this law, so we honor him by calling it Coulomb's law. And I wanted to show the equation like this also, because as you look at different resources, I don't want you to get confused if you ever see capital Q. You'll see that sometimes. Q is Q. Q is going to be charged, whether it's uppercase or lowercase. And also, distance can be represented by R instead of D. Don't be confused by that either. I actually prefer R. Why do I prefer R? Because it's a little bit more three-dimensional. Okay, D, we just think very linearly, just like we did with the lab. Yeah, we're moving the charges this way, back and forth. But R gives us a more three-dimensional thing. Like if my two fists are charged objects, this distance right here is that radius R from my left fist. But if I move this one up here at the same radius, it's the same exact force. Here, here, here. Any distance R away, like on the surface of a sphere, if I were just to walk on a surface of a sphere, I'm going to get the same exact magnitude of force. So R for me seems like a more appropriate one, but you choose whatever. If you like D, stick with D. You can use R, but that's Coulomb's law. Okay, and K is that magic number, like I talked about. And there it is officially, so you know where to look for it if you didn't find it in your text already and you didn't write it down up here. It's in the notes on the PowerPoint here. 9 times 10 to the 9 Newton meter squared per Coulomb squared. Where did that unit even come from? Well, it has to be that, because we have to cancel out our Coulomb squared or our Coulomb squared and our distance squared. So there's newtons left over. But this is a made-up unit. We have no clue what that means. We made up that unit so the units work out in the equation. Legitimately, there's just stuff that we don't know. Science is extremely limited when it comes to some of these universal laws. We just don't know. Any true scientist will still say, what does that number mean? I don't know. There's a lot of theories that we have, but we don't have access to that information. We just have a number for it. And number is the universal language. You can use numbers all day long. Right, so I want you to get out your calculators and I want you to give this a try. See if you can do this problem. So as we work through this problem and apply our Coulomb's law equation, we've got my marker. This electrostatic force is equal to K. So my 9 times 10 to the 9 is my K value. My numerator, I have 50 times 10 to the negative 6. So 50 microcoulombs. I got 1 times 10 to the negative 6 is 1 microcoulomb. All divided by 2 meters squared, the bottom. Okay? And if you put these in your calculator correctly, and I always recommend parentheses. So even here, just put parentheses around things. Otherwise, if I don't put parentheses, your calculator might think that you're multiplying the next number by your power rather than the whole entire scientific notation value. Okay? But if you do this correctly, you should get a number like 0.1, what is it? Hold on. 0.1125 newtons. 0.1125 newtons is what you should get for this particular scenario. One thing I'll point out as I look at this question also is that in some questions, you may not always be given the distance in meters. Okay, but no, you're gonna have to convert to meters. The distance down here has to be in meters. So if you're ever given anything in centimeters, convert it to meters before you use that number in in your calculator. But this is going to be priority number one today. Once we're going back to doing some, when you guys are doing your work, working through some problems, is make sure that you can get 0.1125 newtons for this problem. If you can't, let me know. I'll come over and take a look at what you're doing and make sure that we can get that done. Real quick though, what is the force that exerts Q2 on Q1? It's the same. It's mutual. Whatever force that Q1 exerts to Q2 is the same as Q2 exerting back on Q1. Newton's third law applies here. For every action, there's an equal and opposite reaction. It does apply to added distance forces too. So don't fall into these traps. Sometimes students will think because this is the bigger charge that exerts a greater force. Not true. Okay, the magnitude of the force between these two charges is going to be the same, the 0.1125. So the force that they exert to each other. It would be repulsive. They're both positive charges. I do want to point out that in problems, if it doesn't give positive, like with the number, then it implies that it's positive. If it's negative, it will show negative there, or it will say an electron has, 3 electrons, are here. What's going to be, there's 3 electrons here, 3 electrons here. What's the force between those 2 pockets of electrons? Things like that. Okay. So you've got on today's Canvas page, you'll see that there is a homework assignment. It's 4 problems. That's it. Okay, this Coulomb's law practice. 4 problems for you to practice doing this. I've provided for you answers, so you're not wondering. I really want you guys to be able to get these correct. I don't want you to just do it once and say, oh, I wonder if I got the answer right. I really want you to reference what I have, and your numbers should match my numbers when you do the 4. There's just 4 questions. Guys, do the homework. Quit being so lazy in this class. There's no excuse for it. Okay? No excuse. So please do this homework. You've got time today. Technically, we're done, right? But because there's that last 15 minutes, but I'd like to see you guys working on this assignment so I can help you work through them. Okay?